I am Shaden, and I'll be talking about our work on long-tailed recognition using weight balancing. Many real-world datasets exhibit an imbalanced distribution. For example, here I have 3 real-world datasets. For each plot, the class indices on the x-axis are sorted according to the class frequency. And we can see that some classes have much more samples than others. The problem with imbalanced datasets is that a deep learning model will be biased towards common classes. In this example, we can clearly see that the naive model performs less well on rare classes. However, high recognition accuracy on rare classes is often crucial in various real-world applications, such as autonomous driving and medical image analysis. Many solutions for the class imbalanced learning problem modifies the training data to make it more class balanced. For example, one way is to create synthetic samples and add them to the rare classes. Another way is data resampling, which undersamples common classes or oversamples rare classes. Another idea is emphasizing rare classes in the loss function by giving them larger weights. For our work, we explore the orthogonal direction of weight balancing. To motivate our work, we can start by taking a deep learning model and train it naively on the imbalanced CVPR 100 dataset, which is a modified version of the original CVPR 100, such that it becomes a long-tailed one. Then we can focus at the classification layer, which is the last layer of the network. We can see that the norms of the classifier weights are skewed towards common classes as shown in the plot. And here we can see how the classifier weights are evolving during the training, starting from almost equal randomized weights, which are the blue colors in EPIC 1, to imbalanced ones at the end. This motivates us to balance the network weights by regularizing their norms. We explore 3 techniques to balance weights. First, L2 normalization, second, weight decay, and third, MaxNorm. In L2 normalization, we restrict the classifier weights to have a unit norms, such that if we take a look at the classifier, we can see that it's perfectly balanced. If we take a look at how norms are evolving during the training, we can see that L2 normalization has constant norms during the whole process. The second method is the well-known weight decay, which adds an L2 penalty to the loss function with a coefficient lambda. We found that just tuning weight decay notably improves performance. It raises the performance by more than 8% on these 3 standard long-tailed datasets. We can also see that weight decay helps to learn balanced weights at both the classifier layer and the hidden layers. And here we can see how per class weights evolve during the training, having smaller weights than the naive model. Finally, we have MaxNorm, which caps the weights norms within an L2 ball with radius delta, and to implement it we use projected gradient descent, which ensures that the norms do not exceed that threshold. Here we can see that the norms of a MaxNorm model are almost balanced, and we can see here how the norms are evolving during the training process. We follow the 2-stage training paradigm to carry out an appellation study, where we try different combinations of the previous methods. Based on it, we propose a simple approach to LTR. First, we have feature learning, in which we train a network by using cross-entropy loss and we tune weight decay. Second, we have classifier learning, in which we train a classifier over the learned features using a class-balanced loss, weight decay, and MaxNorm. Using our approach, we achieved 53% accuracy on the long-tailed CVPR 100, and our model achieves higher accuracy for rare classes, in addition to having a balanced norms. Also, by using the same method, we achieved the state-of-the-art performance on CVPR 100 with different imbalance factors. Moreover, we achieved a high performance on the long-tailed ImageNet and iNaturalists. However, it's worth noting that the state-of-the-art methods used in Simple's data augmentation and self-supervised pre-training, which we haven't used any in our simple method. In conclusion, balancing weights greatly improves LTR accuracy, and regularizing the network gives a strong LTR baseline.